Assalamualaikum warahmatullahi wabarakatuh. My name is Ain Atira binti Azlan. So for this video, me and my teammate will present to you about the study that we do from the journal article about the application to the Hplc analysis of aldehydes in oil sample. Before we go further, I will start with the introduction first. Chromatography is a separation technique based on the different interaction of compounds with two phases, which is a mobile phase and a stationary phase, as the compounds travel through a supporting medium in a definite direction. The study article that we study is about an application to the Hplc analysis of aldehydes in oil sample. So, what is Hplc? Hplc is an abbreviation for High Performance Liquid Chromatography. Hplc is the analytical technique that used to separate, identify, or quantify each component in a mixture. The mixture is separated using the basic principle of column chromatography and then identified and quantified by spectroscopy. There are many different detectors that we use in chromatography. Flame ionization, thermal conductivity, and electron capture are some of the commonly used detectors in Hplc. But perhaps the most used detector in liquid chromatography is ultraviolet absorption. A UV detector uses a molecule's ability to absorb ultraviolet light. Detectors can use a single wavelength or variable wavelengths, which can be more sensitive. By passing UV light through the individual component of an eluting sample mix and measuring the amount of UV light absorbed by each component, you can determine the individual quantities of each component. Principle of Hplc is started with the solute being injected onto the top of column. When the analytes and mobile phase were pumped through the column, the separation process will occur. Each of the component class from the column as peak on the recorder. As the result, the chromatogram was displayed. In this experiment, the NPH derivatized aldehydes are quantified by Hplc UV methods or LC-MS methods. The NPH is the most used derivatizing reagent for aldehydes, and the form hydrogens could be determined by either Hplc UV or LC-MS.
Today, I will be presenting about methodology. First, target aldehyde stock solution was separately prepared using acetonitrile as a solvent. Second, a standard mixture of the targeted aldehyde was prepared in acetonitrile. Stock DNPH solution was prepared in acetonitrile. Then, a working solution of DNPH was prepared through tenfold dilution of the stock DNPH solution in hydrochloric acid. Mixed aldehyde standard solution was stored at negative 20 degrees Celsius, while all other solution was stored at 4 degrees Celsius in the refrigerator. A pH meter, a sonicator, and automatic mixer were used for pH measurement, sonication, and mixing respectively. Hplc analysis were performed employing online UV irradiation luminol CL reaction and followed by CL detection. The analysis system consisted of 3 LC-10AS liquid chromatography pumps, an injector with a sample load volume of 20 microliter, and an online photoreactor consisted of a reaction coil coiled on a 10-watt 254 nanometer low pressure mercury lamp, maintained at room temperature in a black box placed after the chromatography column. Secondary coil is introduced after the reaction coil for decreasing the background noise. A detector and a chromatopro data acquisition system were used for CL detection and data acquisition respectively. The chromatographic separation was performed at room temperature on a column using mobile phase consisted of acetonitrile and borate buffer in the ratio of 55/45. After the chromatographic separation, the post-column eluate was alkalinized with sodium hydroxide prior to UV irradiation, followed by the online reaction with luminol and then CL detection. The flow rates of the mobile phase, sodium hydroxide solution, and luminol solution were 1.0, 0.2, and 0.5 milliliter per minute respectively.
I will present about the results of this case study. Firstly, the effects of different factors affecting the online UV irradiation luminal chemiluminescence reactions of DNPH hexagonal derivative were studied through an experiment to see their influence on relative peak area and signal to noise ratio. Firstly, the UV irradiation reaction coil length was studied over the range of 1 until 8 meter, and it was found that CL intensity increases with the increase in the coil length. However, the best signal to noise ratio was obtained using a 6 meter coil. Then, the UV lamp watt 10 and 15 watt and wavelength 254 and 365 nanometer were tested, and the best signal to noise ratio was obtained using 10 watt 254 nanometer UV lamp. Next, the concentration of sodium hydroxide solution used to alkalinize the eluate prior to UV irradiation was studied over the concentration range of 5 until 50 mm. The CL intensity increased with the increase in sodium concentration. However, the noise also increases. Thus, 20 mm of sodium hydroxide was used in further studies as it yielded the highest signal to noise ratio. Then, the length of the second coil was studied, and as shown in the graph. As the coil length increases, the CL intensity decreases. However, the signal to noise ratio increased with the coil length increase and reached a maximum at coil length of 12 meter. Lastly, the luminal solution alkalinity and concentration were studied over the concentration ranges of 20 until 400 mm of sodium hydroxide and 0.05 until 25 micrometer luminol, respectively. The best results in terms of signal to noise ratio and CL intensity were obtained using 10 mm of luminol dissolved in 300 mm of sodium hydroxide as shown in the graph. For the next results based on the graphs is to test the reliability of the developed Hplc CL method for DNPH derivatized aldehydes. We intended to apply it for the determination of aldehydes in oil samples. The graph shows chromatograms of A, which is fresh canola oil, graph B, spiked canola oil injected in concentration of 5 micrometer, graph C, 10 minutes of heated canola, and D, 30-minute heated canola, where peaks from 1 to 5 are propanol, butanol, HNE, pentanol, and hexanol respectively, but only graph A, propanol is present.
Aldehydes are hazardous carbonic chemicals found in a variety of materials around us. For examples, aldehydes may be generated during the cooking and frying of foods, affecting the quality and safety of the food. Because aldehydes lack intrinsic chromophoric groups, derivatization is required for identification. The most often used derivatizing reagent for aldehydes is 2,4-dimetrophenylhydrazine, or we call it as DNPH. When exposed to UV light, single oxygen is generated, which subsequently transforms the DNPH aldehyde derivative to hydroperoxide. The hydroperoxides then interact with luminol in an alkaline medium, resulting in a strong CL. And Hplc system with online UV irradiation and online luminol reaction, followed by CL detection, was built and utilized to determine aldehydes following derivatization with DNPH. The new approach demonstrated high sensitivity with detection limits as low as 1.5 to 18.5 nanomolar to sensitivity gain is higher than that obtained by Hplc UV and LC-MS detection techniques for the NPH aldehydes derivative. Furthermore, this method is cheminogenic, which means that the NPH reagent does not create Cl on its own, which is significant benefit. The methodology was effectively used to determine aldehydes in canola oil samples using simple liquid-liquid extraction. With high recovery, 87 to 106%, accuracy at 87.2 to 106.6%, and precision 10 to 2%. The study of fresh and heated oil samples revealed the heating oil, even for a short period of time, significantly increased the amount of aldehyde content. Finally, it was discovered that the findings of the suggested techniques analysis of aldehydes in oil samples precisely matched those obtained by a reference LC-MS method. During this experiment, we can make an analysis of fresh and heated canola oil samples. Fresh canola oil samples were examined as is after being heated at 180 Celsius for 10 to 30 minutes and after being spiked with the desired aldehydes. The aldehydes in the oil samples were then extracted with acetonitrile and derivative with the NPH. The peak areas of aldehydes extracted from spiked oil samples were compared to those of reference combination in a recovery investigation. The recovery percentage varied from 87 to 106.1%, which is extremely comparable to the accuracy data. Demonstrating the good performance of the liquid-liquid extraction technique used. Only propanol was discovered in the non-heated oil samples, whereas other aldehyde levels were lower below this method's detection limit. Following that, heating oil samples for only 10 minutes resulted in a substantial rise in aldehyde levels, which varied from 6.6 molar for HNE to 256.3 molar for propanol. When the heating duration was increased from 10 to 30 minutes, the aldehyde levels increased by roughly 1.1 to 3.7 times. The creation of aldehydes during the heating of canola oil is related to an increase in both fatty acid synthesis and oxidation, which result in high amounts of aldehydes. The quantitative values obtained by the proposed Hplc-CL method acknowledge well among obtained by the LC-MS method for all aldehydes at different heating times, and no significant difference is observed using the paired students TT test. For example, P equals to 0.8064 and variance ratio F test P equals to 0.4770. As a result, the established Hplc-CL method's dependability, accuracy and precision were convincingly proved. In summary, heating oil causes thermal oxidation of fatty acids, which results in the formation of several volatile organic compounds, the most notable of which are aldehydes. Edible oils such as canola oils are high in nutrient and include a variety of fatty acids. These fatty acids might be oxidatively decomposed by heating and long-term storage at high temperatures, producing aldehydes with a disagreeable odor. Furthermore, some of the aldehydes generated are extremely hazardous to consumer. Therefore, examination of aldehydes in edible oil, whether fresh or heated, is essential for monitoring the quality and safety of these oils for human consumption.
In conclusion, in this experiment, the high-performance liquid chromatography method was used to determine 2,4-dinitrophenyl-hydrazine. The aldehyde reacted with singlet oxygen that produced. As a result, it converts to hydroperoxide, which causes strong Cl when mixed with luminol, but a clean chromatography free of a reagent blend is obtained due to the lack of hydrazone due to the NPH not providing substantial Cl. It eliminates the requirement for extra reagent to be extracted from sample. because this technique is constructed by three things, which is online UV irradiation, online luminal reaction, and chemiluminescent detections of the NPH has a derivative. By that, they have several factors that affecting. The first factor is the coil and the UV lamp factor, where it can be concluded that the best signal to noise ratio was obtained using a 6-meter coil, while the best signal to noise ratio was acquired using a 10-watt 254 nanometer UV lamp based on the relative peak area and signal to noise ratio that can be seen on the graph. Furthermore, the irradiation alkaline 20 millimolar sodium hydroxide was utilized in future tests since it provided the higher signal to noise ratio. Whereas for the length of the second coil, the signal and noise ratio increased with coil length and reached at 12 meter. The alkalinity and the concentrations of the luminal solution were obtained using 10 micrometer luminol dissolved in 300 millimolar sodium hydroxide as the final factor. To conclude, when determining aldehyde in canola oil sample using simple liquid-liquid extraction, the recovery percent range from 87 to 100.6.1%, which is very similar to the accuracy data, implied that this Hplc was successful because short-term heating of the oil significantly increased the aldehyde's content level. Propanol was found in non-heated oil samples while the level of other aldehyde were lower. However, after heating the oil sample for 10 minutes, the level of aldehyde increased, with value ranging from 6.6 micrometer for HNE to 256.3 micrometer for propanol. The aldehyde level increased 1.1 to 3.7-fold when the heating period was increased from 10 to 13 minutes.